right, and we're back, folks. So this is just a little application of, kind of a little bit of a linear approximation example, as well as what we've been doing with our graphing here, okay? This doesn't really fit in a lot. It's just kind of like, okay, now that we know how to do all of the things that we've been doing, let's do this too. It's called Newton's method, and basically it's Newton's method for finding zeros. Okay, that's basically what it is. It's Newton's method for finding zeros of a function. Okay, let's take a look here. The book presents this example. Suppose that a car dealer offers to sell you a car for $18,000 for payments of $375 per month for 5 years. You'd like to know what monthly interest rate the dealer is in effect charging you. To find the answer, you would have to find the solution to this equation. That seems like a pretty intricate equation to solve, right? You may be thinking, oh, well, maybe I could somehow use the derivative to find it, but still, finding the derivative, you got some weird chain rule stuff going on with a product rule at the beginning. It's not a very easy equation to solve. We would not be able to use a quadratic equation because obviously this is not quadratic, right? For a quadratic equation, ax squared plus bx plus c equals 0, there's a very well-known formula. If it's a quadratic, you could just pop in the quadratic formula, easy, done. Those are your answers, okay? For third and fourth degree equations, there are also formulas, and there are also ways around solving it, but they're still pretty difficult. There's not really one set way to do each type of problem. They're pretty complicated. Now, if f is a polynomial of degree 5 or higher, there is no such formula. Right? There is no formula, straight up formula to solve for roots. Likewise, there's no formula that will enable us to find the exact roots of such equations like cosine x is equal to x. We'll look at that. That's example 3. If you've got an equation cosine x is equal to x, there's no real equation to solve for that. You may be thinking, oh, well, I would just take inverse cosine of the other side, but then you would have x is equal to inverse cosine of x. And then how do you solve that? Or maybe how do you, there's no one set way to solve that one. So what we're going to do is, what Newton came up with is finding approximate solutions to these things using calculus. Using calculus to find approximate solutions. We can find approximate solution for equation 1 by basically plotting the left side of the equation, using a graphing device, and after experimenting, we would produce a graph. I didn't capture over figure 1, but basically, you can estimate what that is. Now, what your calculator actually does, it's not actually using any sort of formula to find the zero of the function. When you go in your calculator, you use second calculate 0. It's not actually using any type of formula. It's not actually running the quadratic formula or anything like that. What it's using is actually called what it's called Newton's method. And let me show you graphically what's happening. Say you had any function. Say you had any function. This is f of x here. Take a look at figure 2 here. You got this curve. And you know that it crosses the x-axis. You know there is a 0. You know a 0 does exist. There's points below the x-axis, and then there's points above the x-axis, but you don't know how to solve that equation, or there's not a set way to solve that equation, to solve for the 0 of that equation. What we can do is actually use the linear approximation. We can actually use the linear approximation, which is this formula down here. Okay? We can actually use the linear approximation to kind of narrow our focus a little bit, to try to get closer and closer and closer toward it. Like, for example, here, if I use a linear approximation at point x1, okay, that's meaning I'm finding the straight line that lies tangent to that curve at that coordinate. I'm finding the equation of the straight line function that lies tangent to that function. And what we can do is find the 0 of that, right? The linear approximation will say, okay, well, here's the equation that lies tangent to the curve at that point. And what you can do is find the 0 of that. Now, it gets you pretty close to what the root is, but there's still some distance away. There's still a little bit of error there. So what can we do? Well, what if we get closer? And then it would be right there. What if we get closer? And then it would be right there. So what we're going to be doing is we're going to be taking points closer and closer and closer to the root until we can get a really good approximation of what that is. Okay? To find a formula for x2 in terms of x1, we use the fact that the slope of the line L is f prime, right? We know that the slope of the tangent line is the derivative at that coordinate. So the equation is y minus f of x1 is equal to f prime of x1 times x minus x1. That's just the linear approximation formula. It's basically point slope, right? That's point slope at x1. Okay, that's point slope at x1, where the slope is f prime at that point. Okay. Now, here's the deal. We want the 0 of that linear function, though. Well, the coordinate for the 0 of that linear function is x1 comma 0, right? So the y value is going to turn into 0. And then what we can do with a little manipulation is turn it into this. x2 is, if I distribute in, if I divide over, if I divide f prime over, and then I add over the x1 or subtract over, or no, add over the x1, I'm going to get this equation where x2 is actually equal to x1 minus f divided by f prime. Okay? So what we've done here is we've actually rewritten our second term in this sequence with using x1, okay, using our first approximation. We said, okay, we think x1 is going to be somewhere close to this. We think the root's going to be somewhere close to that. And then we say, okay, we can find x2, something a little closer, using x1. If we take x1 minus f of x1 divided by f prime of x1. And we could keep that process going. If I wanted to keep that movement going, keep getting closer and closer to the root, I could say, well then, if I just make this arbitrary, I can say that x sub n plus 1 is equal to the term before it, x sub n, minus plugging that value into the original function, divided by plugging that value into the derivative. And that is Newton's method for approximating a 0. This is Newton's method for approximating a 0. You start with your first guess, your best guess at what you think the 0 is. That's your x1. And then you just got to keep going through the process. You got to keep plugging and chugging. You got to plug x1 into that formula. It'll give you x2. You got to plug x2 into that formula. It'll give you x3. You got to plug x3 into that formula. It'll give you x4. And you keep that process going until you find a good approximation. Okay? You keep that process going until you find a good approximation, meaning you keep that process going until you see where it will converge to, right? Soon enough, it'll go toward a certain number. It will level off toward a certain number. So you can at that point say, well, it looks like it's going to converge to this value. Looks like it's going to be this decimal value. Let me show you how. All right, we've got this function x to the third minus 2x minus 5. I want to find the 0 in it. You know, without a graphing device, without a graphing calculator, there is no way to solve this function, to solve the 0. I've got x to the third minus 2x minus 5. Without a graphing calculator, see, in Algebra 2, we teach you, if it's not quadratic, you go to your graphing calculator and you try to synthetically divide out one of the roots to see if you can get it to reduce down. But what if it doesn't even do that? What if we cannot find a root to reduce it down? Well, we can approximate the solutions. Now, I need my sheet. Now, the formula again is x2 or xn plus 1 is equal to xn minus f of xn divided by f prime of xn. Okay? That's the formula, and we derived that from the linear approximation formula. So what does that mean? That means that f of x is going to be x to the third minus 2x minus 5. And f prime of x is going to be 3x squared minus 2. Right, I find f and I find f prime. And then I start the process with x1. I say, okay, I believe that it's going to be close to 2. Maybe I looked at my graphing calculator or somehow found, I think it's going to be pretty close to 2. Let's see what happens when we plug in 2. Well, x1 is 2. So x2 is x1 minus f of x1 divided by f prime of x1. Do we know what all those things are? Yeah. x1 is 2. Then we're going to find f of 2 and f prime of 2. Okay. So it's going to be f of 2 is 2 to the third minus 2 times 2 minus 5. So I got negative 1 up top. So that's going to be 2 minus a negative 1 divided by f prime of 2. 3 times 2 squared minus 2. 10. Okay, so this is going to be 2 plus 1/10, so 2.1. So x2 is 2.1. Let's find x3. Yeah.
Do you use the plus one, like the on the left side where it says x to them plus 1?
That's just the next term in the sequence.
Okay.
So if I want x2, that's really like x sub 1 plus 1, right? Yeah.
Is that like the subscript, the plus 1?
Yeah. Down below. Yeah. This is like I don't know if you guys know this term, a recursive formula. Basically using the previous piece of the sequence to define the next one. Okay. So like if I could keep going here, I would write x3 is going to be x2, x sub 2, minus f of x sub 2 over f prime of x sub 2. But we know what x sub 2 is. It's 2.1. So we say that's 2.1 minus f of 2.1 divided by f prime of 2.1. So let's run the numbers. Let's see what it is. So I got to take f of 2.1. So x to the third, so 2.1 to the third, minus 2 times 2.1. Minus 5. We're going to take that divided by, I'll do the whole thing in the calculator, divided by f prime of 2.1. 3 times 2.1 squared minus 2. That's f of 2.1 divided by f prime of 2.1. So it's 2.1 minus this. Right? That decimal is this piece over here. So 2.1 minus my answer. 2.095. Yeah, that's what I got here. 2.095. So x3 is 2.095. And that's what it asked for. Find the third approximation to that root. So the third approximation is 2.095. If we kept that process going, we would see that maybe the next set is still a, instead of 2.095, 2.095,681, maybe it's 2.095,68, whatever. Maybe it varies just a little bit. So we can say, round off the error there, it's about 2.095. Okay. Just converging to that number. Yeah. Yeah. I'll always have to give you, like in the next example, it says correct to 8 decimal places, right? So what we can do, right? Suppose that we want to achieve a given accuracy to say 8 decimal places. We could keep that process going until we get out to 8 decimal places and there is no change between xn to xn plus 1. Okay, so you can achieve an accuracy up to any decimal places. I think in the homework, some of them are like, achieve it to 4 decimal places. This one says achieve it to 8 decimal places using Newton's method. Okay, how do you know when to stop? Well, basically, you know when to stop when you calculate x sub n, and then you calculate x sub n plus 1, and they are the same to the 8 decimal place out. Okay, that's when you know to stop. You can say, okay, we'll round off the rest, correct to 8 decimal places. That's where we can stop. Okay, so let's try it here. Now, we have to make a function out of this thing. Use Newton's method to find the 6th root of 2. The 6th root of 2, correct to 8 decimal places. I have to create a function of this thing. Because what I'm going to do is find the zeros of that function. Well, to find a function, I first need to really just set it equal to x. I say, well, x is equal to the 6th root of 2. And let's get this thing set equal to 0, because that's what Newton's method will do. It will find a 0. It will find approximations for the 0. Well, if I'm taking the 6th root of something to get it over to the other side, I got to take it to the 6th power. X to the 6th is equal to 2, and then I can subtract over the 2. X to the 6th minus 2 is equal to 0. That's the function. That's the function that we're going to use. F of x is equal to x to the 6th minus 2. So now let's find its derivative, because we're going to need it. The derivative of that, f prime of x, is 6x to the 5th. And the minus 2 goes away. Now, so we've gotten just about every piece, right? If I want to find x sub 2, it's x sub 1 minus f of x sub 1 over f prime of x sub 1, right? But I need somewhere to start. Try to do it loud. But where do I start? Where is x sub 1, right? Well, what you have to do is create the best possible guess. Create the best possible guess for you to use. You could make it a decimal place if you wanted to. Like the book Key uses a decimal place for a lot of the homework answers. Like for our purposes here, just to show you what I would do. Like my reasoning is, well, think about like, if I wanted the, if I'm looking at the 6th root, I've got to believe that this is somewhere between 1 and 2, right? This is somewhere in between 1 and 2. The 6th root of 2 is somewhere between 1 and 2. Because the 6th root of 1 would obviously be 1. And if I go the 6th root of 3, that's got to be somewhere above that value. So I got to think that the 6th root of 2 is somewhere like 1. You really kind of just guess at it. Honestly, you really just guess at it. And the better guesser you are, the quicker you're going to get to 8 decimal places correct. Yeah. So what the book's Key does for the homework problems is it hones in a little bit further and it tries to give it to the best decimal place. Like they round it to the nearest 10th. They try to guess it to the nearest 10th. so that it just takes a little bit less like times you have to do this. Like for our purposes here, if I just say x equals 1, x1 equals 1, x1 equals 1, it's going to take us a little bit. It's actually going to take us 6 iterations of this thing to find it correct at 8 decimal places. Okay? So again, let's try it at 1. 1 minus f of 1 over f prime of 1. And we run the numbers. Okay, well, 1 minus, let's plug this in. Let's do the whole thing so that I can just plug in numbers in the end. 1 minus, and then I've got to find f of 1. Well, f is x to the 6th minus 2. X to the 6th, so 1 to the 6th. I'm using parentheses because I'm going to have to go in and change it in a second. X to the 6th minus 2. That's my numerator, right? Divided by f prime of 1. So I'm going to go plug it into f prime. 6x to the 5th. All right, 6, 1 to the 5th. Oh, yeah, and my parenthesis here, I don't need this one. Just to be sure that this is going to calculate correct, I'm going to put a parenthesis on the bottom. I'm going to insert a parenthesis right here and end it right there. Because I want it to calculate the whole bottom, then divide. Do I feel like I should, yeah, because it might try to divide by 6.
Yeah.
Then multiply. Yeah, I need that. 6 times 1 to the 5th. Okay, let's run. 1.16. Good. I match. So x2 is 1.16 repeating. I could write it out to 8 decimal places, but it's 6 is over there. Let's find x3. Well, the reason I put in that whole formula here is because now I can just like copy paste. Second entry will get me my last run function. So what I'm going to do is go insert, instead of 1, all the places where I plugged in 1, I'm going to plug in my answer. Second answer. Second answer. Second answer. Because that's going to take 1.16 and plug it in everywhere. $1.1264438. Yep, that's exactly what I have. 1.12. I'll just write it from here. 1.1264438. 1, 2, 3, 4, 5, 6, 7, 8 decimal places out. All right, let's run x4. How do I run x4? Well, I'm going to plug in x3 into my function. I'm actually just going to do that, because that is going to run the last answer that I had into that function again. So now when I hit that, boop. Okay, I'm getting closer. It's converging toward a number. 1.2249707. Yep. 1.2249707. So right now I'm correct to 1.122. Yep. Right now I am correct to 2 decimal places out. You see how I'm matching to 2 decimal places? I've got to get to 8. So let's keep it rolling. Okay. 0.5, yep. 1.12246.205. Okay, how many am I good to now? Let me highlight it so you see what I'm talking about. Okay, so I was 1.12, 1.12 here. Now I'm at 1.1224. I'm good to 4 decimal places out right now. Let's keep it going. One point one two two four six two zero four. 1.122462048. Round up. Fine. Do you see how it matches to 8 decimal places out? So therefore I know that's a very, very good, I mean, for any purposes that you have, that's a really good approximation of that root. Okay. Probably to the near, I mean, going 4 decimal places, that was probably really good, but still. Okay. So what are we doing here? What is this? This is, again, just finding the approximation of that root. This is all your calculator is doing. When you hit second calculate, find the 0, this is what your calculator is doing. It's just doing it really fast. Yeah. It would have converged backward, yeah.
It would have gone backwards?
Yeah. Yeah. Because the minus then turns it into a plus. You know, it'll go negative and it'll go backward to it. Okay, find correct to the 6 decimal places the root of the equation cosine x is equal to x. Yes?
How are you doing that with your calculator to get it to?
I inputted the entire function, the entire thing, the x1 minus f of x over f prime, using my 1 first, and then I just kept inputting my answer. Answer minus, plugged in answer to f. This is like answer minus f of answer divided by f prime of answer. Does that make sense?
Yeah.
Okay. Let's try that again. Find correct to 6. So I don't need to go to 8, just 6. Correct to 6 decimal places. The solution to the equation cosine x is equal to x. See, I can't solve this algebraically, right? There's no way I could possibly solve this algebraically. Cosine x is equal to x. I don't know. I don't even know where to begin. We'll take a look at where to begin in a second. All right, but what we do need is cosine x is equal to x. We need a function to solve for. Well, again, Newton's method uses the function, uses zeros, right? So I've got to set it equal to 0. I can say cosine x minus x is equal to 0. So that's f. F of x is equal to cosine x minus x. So what is f prime then? Well, negative sine x minus 1. Okay, so if I'm setting up my equation, it's x2 is going to be x1 minus f cosine x minus x divided by negative sine x minus 1. I'm just going to do something to simplify it a little bit so that we can plug it in a little bit easier. Do you see how I can pull out a negative 1 on the bottom? We're going to do that and pull it out and make it a plus. x1 plus cosine x minus x over sine x plus 1. Okay, it's just to make it easier to plug in. Pull out a negative 1 on the denominator. Okay, so where do we start? Where do I find x1? Well, the book says, well, maybe let's try to find graphically where these things end up. Like cosine of x and just x. Let's see, let's make this like a system of equations and see where these things are going to cross. Because honestly, look what I've got here. Cosine of x and x. Okay, so that's my cosine curve. And then y equals x is just like a diagonal line running through the first and thirds. So there's cosine. Okay. Now, the best whole number I'm going to go at, see, and actually this is to kind of show you, I went low and it got me to the point higher. I'm going to show you here. It looks like it's pretty close to 1, right? But it looks like it's a little bit bigger than 1. I want to show you that if I start at 1, it's going to bring me back to the function. It's going to bring me back to the 0. Okay? And the reason I'm doing this is because doesn't it look like it's closer to 1 than 0? It looks like it's closer to 1 than it is to 0. So I'm going to start at x1 equals 1. Okay? And again, this is to kind of show you that, yeah, it'll bring me back to it. I don't need to start lower than it. I just need to start above it or below it. It doesn't matter. Okay, so x2, therefore, is going to be 1 minus cosine of 1 minus 1. 1 plus cosine of 1 minus 1, sine of 1 plus 1. I got to be careful there. That 1 is a constant, not an x. When I go to plug my answer in, I just got to be careful with that. So I'm going to go out to my home screen, and I'm going to be very careful when I plug this in. I've got 1 plus, okay, in my numerator, cosine of 1 minus 1 divided by, start my parenthesis, sine of 1 plus 1, and my parenthesis. Everybody see what I'm doing there? I'm just plugging the entire function in. Because now when I hit enter, 0.75036, okay, so I only need to go how many places? 6 decimal places. So 0.75036. Let's go to 8 so that we can see that it varies afterward. 1, 2, 3, 4, 5, 3, 8, 7. It doesn't matter at that point, out beyond where I care about. Right? Should I round it up?
Yeah.
Yeah. It doesn't matter past 6. Okay, so let's find x3. Okay, I'm going to go in and I'm going to plug in answer. Now be careful. I'm going to go in here and I'm going to plug in second answer plus cosine of, it was cosine x minus x. So answer here. Answer here. Be careful. I only want to plug in answer to the sign because that plus 1 was constant. It wasn't sine of x plus x. It was sine of x plus 1. Okay, so 0.739.739112. That's 6. Let's go 2 more out. 89. So right now I'm only correct to 1 decimal place out. Right, I'm only accurate to 1 decimal place. The only things that match between x2 and x3 are the 0.7. Beyond that, they don't match. So let's run it again. Make sure it matches. Yep. 0.7 x4 is 0.739085513. I'm correct to 3 decimal places. So let's run it again. I need to get to 6, right? To 6 decimal places. Okay, 0.739 x5 is 0.739085513. Oh, I got to 6 and 8 at the same time. So I know that intersection point is x equals, to correct to 6 decimal places, x equals 0.739085. Yes.
Would each repetition here was confirmed in 1 decimal?
Not necessarily, like, cause it jumped. I was only good to the 10th place. And then I got to 3 decimal places out in the next one. And then I went from 3 all the way out to 8. You're getting exponentially closer to it each iteration you do. What's that?
You said as many as repeat, how do you know which decimals?
As many that repeat. Yeah, because I see, oops, I went too far. Like, that was the only stuff that was the same between one to the next. But then, look here, it got all the way out to the end, from here to here. Does that make sense? The answer is what the solution is, right?
Is it X or is it X4 or is it X5?
Well, what is the goal? The goal is to find X. Right, X equals that. It took us 5 iterations of Newton's method to do that. But it's X equals that thing. Okay. Questions about that? Okay. All right, let me stop the video.